Hey there, Keys Pre-Calculus. This is the promised video for 8.3, Geometric Sequences and Series. We learned about arithmetic sequences and series in the last class, and this is just a continuation of that. They're similar, but not quite the same, because in an arithmetic sequence or series, the terms, each consecutive term has a common difference. But in a geometric sequence or series, each term, or each consecutive term, has a common ratio. In other words, if you take the second term and divide it by the first term, that should be equivalent to the same thing as the third term divided by the second, or the fourth term divided by the third, all the way to the nth term divided by the term in front of it, which should be r. R is a common ratio. It can be, it's any rational number. It can be expressed as a whole number, or a rational number, or an integer that's negative, or a rational number that's negative. The only thing it can't be is 0, or irrational. So let's look at some examples. So if we take this first example A here, if I take 4 and divide it by 2, is that the same thing as saying 8 divided by 4, or 16 divided by 8? Well, they each equal or equivalent to 2, right? So it is geometric, because if a sequence is geometric, the ratios of consecutive terms are the same, and in this case, these ratios are the same. So remember, ratio is just a fraction. So my r here is the same for all of them, and it is 2. So let's look at the second one here. The second one, if I take 36 and I divide it by 12, that gives me 3. And if I take 108 divided by 36, that's also 3. And 124, I didn't write 124, I meant to write 324. It's like, oh, that's not going to work. 324 divided by 108 is also equal to 3. Or I could say 12 times 3 is 36. 36 times 3 is 108. 108 times 3 is 324, and so forth. So this all has a common ratio of 3. Now, let's look at the green one. Let's see if it's geometric. So I take 1/9 and I divide it by negative 1/3, which is the same thing as saying multiplying by 3/1. Negative 1/3 multiplied by negative 3/1, which gives me a negative 1/3. And then if I take negative 1/27 and I divide it by 1/9, which is the same thing as multiplying it by 9/1, I also get a negative 1/3. And then let's do the last one. 1/81 divided by negative 1/27, which is the same thing as multiplying by 27/1, gives me also a negative 1/3. So I do have a common ratio, and it is negative 1/3. Or another way you could think of it is negative 1/3 times negative 1/3 is 1/9. And 1/9 times negative 1/3 is negative 1/27. And negative 1/27 times negative 1/3 is 1/81. And the same thing, I didn't say that for the blue one, but 2 times 4 is 2, 4 times 2 is 8, 8 times 2 is 16. You can see that all the way to the rule. Now let's look at this last one, the orange one here. Let's see if I can change my color here and go to this one. 4 divided by 1 is 4. 9 divided by 4 is not 4. It's 9/4, or 2 1/4. 16 divided by 9 is not 4. So these do not have a common ratio. Therefore, it is not a geometric sequence. Even though it's got a base that's squared, it's not a geometric sequence, because what I need is my base to be the common ratio, and then raised to the n power. Just like you see up here in these other rules. The blue rule is the base, the common ratio 2 to the n. Here, the pink one is the common ratio 3 raised to the n power, the whole thing multiplied by 4. And then here, on the green one, it's the common ratio negative 1/3 raised to the n power. D is different. It's n raised to the second power, which does not give you a geometric sequence. Okay, so now we're going to add a couple more formulas to your list. And the first one is how you find the nth term of a geometric sequence. It's just simply a sub n equals the first term times the common ratio raised to the n minus first power. So in other words, a sub 1 here, the first term, let's see if I can show you with my cursor here. A sub 1, and again, I don't know what's showing on your screen, but I'm trying to circle it with my finger here. The first term is just the first term times the common ratio raised to the 0 power, which is just the first term times 1, or just the first term. The second term would be the first term raised to, or multiplied by the common ratio times 1. So n minus 1 is 1 because 2 minus 1 is 1. The third term, so n is 3, is just the first term times the common ratio raised to the second power, or 3 minus 1. And so forth, all the way down to the nth term would be the first term times the common ratio raised to the n minus 1, which is the formula. So if we go back and we look at the first example that the A that we looked at, we had not 4, sorry. It started, I believe, with a 2, and then the second term was 4, and the third term was 8, the fourth term was 16, and so forth. So basically the first term is just 2 times the common difference, which we learned was 2, raised to the second power, which is just 2, times 1, which is just 2. And the second term is the first term times the common difference raised to 2 minus 1 is 1. So basically it's 2 times 2, which is 4. The third term is the first term times the common difference raised to the 3 minus 1 squared, because I'm multiplying it by another r each time. So that's why I can use the exponent 2, or 2, 3, 4, and so forth. I can use exponent n. So 2 times 4 is 8. And see how I see it? Every single time I'm using my first term times the common ratio, which is 2, raised to, this in other words is 4 minus 1, which is 3. 2 to the third is 8. So I get 16. So are you seeing that here I'm taking, after the first term, I'm taking the term before it, so the term before the first term, the term before the second term, I'm sorry, is 2, and multiplying it by 2. And then I'm taking my 4 up here, and I'm multiplying by 2. And I'm taking my 8 and multiplying it by 2, which leads to the fact that if you know the nth term of a geometric sequence, then its recursion formula, which they don't supposedly call it that, but you can find the next term. You could say the next term would just be the term before it, a sub n, times r. Or I believe your book writes it with those two numbers reversed. A sub n plus 1 is equal to r times the term before it, a sub n. So here is another formula that you can add to your list of formulas. It's not derived from the pink example. I was just using the pink example to show you, to illustrate how if you know the nth term of a geometric sequence, then you can find the next term just by multiplying it by the common ratio. Okay, I'm going to let you study example 3 on page 577 on your own, so just pause the video and look at that. It's quite simple. I'm not going to go over it with you here, but just study that, and then we're going to look at example 3 together, which is also fairly simple if you just use the formula. So it says, find the 15th term of the geometric series whose first term is 20 and whose common ratio is 1.05. So we've got our first term is equaling 20, and our common ratio is equaling 1.05. We could do like you do in example 2, and we could find the first 20 terms by saying 20 times 1.05 for the second term. And then the third term, that number, which was the second term, times 1.05 again, and so forth and so on. Or we could just find the 15th term by following this formula over here. A sub n equals, that I have on the right side in pink. A sub n equals the first term times the common ratio raised to the n minus 1. So since I'm looking for the 15th term, I'm going to say a sub 15 equals the first term, which is 20, times the common ratio, which is 1.05, raised to, since I'm saying the 15th term, I need to say 15 minus 1, or to the 14th power, so 20 times 1.05 raised to the 14th power. And when I multiply that all out, or use my calculator, I'm not going to multiply it all out, I'm going to use my calculator, I get the number 39,599. So the 15th term of this geometric sequence is 39,599. Example 4 works almost the same way, only they don't give you the ratio. They give you the sequence that starts with 5, 15, 45, and tell you it's geometric, and they say find the 9th term. So in order to find the 9th term, we first have to find the common ratio. Well, if we say 15 divided by 5, that's 3. 45 divided by 5, that's 3. So 5 is 3 is 15. 15. So we see that the common ratio, we find it by dividing, and we find that it's 3. So the 9th term is going to be the first term, 5, times 3, which is the common ratio, raised to the 9 minus 1, which is 8. Or not 8, but 8. Okay, when we multiply all that on our calculators, we get that the 9th term is 32,000, and not multiply it out, but when we plug it in to our calculators, we get 32,805. So the 9th term of this geometric sequence is 32,805. You see that it ratchets up very, very quickly. The numbers grow because we are dealing with exponents. So example 5 on page 578 is a little more complicated. They don't give us the first term, and they don't give us a sequence of terms, so we can't find the common ratio quite as simply. So they tell us the 4th term is 125, and the 10th term is 125 divided by 64, and they want us to find the 14th term. So we're going to have to find out how the 10th term is related to the 4th term. And we're going to do that by using this n-term formula right here, but we're going to use it with the n being 10, and my n minus 1 being 10 minus 4. So this is how I'm going to say a sub 10 equals not a sub 1, but a sub 4 times r to the, instead of n minus 1, I'm going to say 10, because that would be my n, minus 4, because that's in the place that 1 was. My a sub 10 is 125 over 64, and my a sub 4 is 125. I do not know my r, but that's what I'm looking for, raised to the 6th power. Now, in order to solve this, I'm going to divide both sides by 125, and I'm going to switch sides. So I'm going to get r to the 6th equals 125 64ths divided by 125 is the same thing as saying 1 over 64. And now to solve for r, I need to take the 6th root of both sides. And then when I do that, I get r equals 1/2, because 2 raised to the 6th power is 64. And since I'm multiplying, it's a common ratio, I'm just going to use the positive, because the problem tells us to assume that all the numbers in the sequence are positive. So now that I've found my r, I can find my 14th term. Again, using my nth term formula, but I can't use my first number because I don't know what my first term is. So I'm going to have to go back to one of the other terms. I can either use the a sub 4 or I could use the a sub 10. I'm going to do both so that you can see that it works no matter which one you use. So the first one here, I'm going to do a sub 14 is equivalent to a sub 10 times r raised to the 10, or not 10, but 14, because 14 is my n, 14 minus 10. So really, I'm going to say a sub 14 is equal to 125 over 64 times my r, which is 1/2, raised to the 4th power. And when I simplify it and sub it all the way down, then I'm going to get, I should get 125 over 1024. If I raise 1/2 to the 4th power, then multiply it by 125 over 6, this is the number that I get. And that is my 14th term. I could also solve it using the 4th term. So I would say a sub 14 is equivalent to a sub 4 times r raised to the 14 minus 4. Because I'm using my 4th term, so this is the 14 minus the 4. So a sub 14 equals my 4th term, which is 125, times my common ratio, which is 1/2, raised to the 10th. And when I plug all this in my calculator, I get the same number. I get 125 over 1024. So no matter which one I use, I will get my 14th term being 125 over 1024. And this is how you find the nth term of a geometric sequence, whether or not you know the first term. As long as you know a couple of the terms, you can do it. In other words, if you know any two terms, and they don't have to be consecutive, but any two terms of a geometric sequence, you can use that information to find a formula for the nth term, and you can find the nth term. It is easier if they're consecutive, but if they're not, you can do what we did here. Okay, so the next thing that we're going to learn is the formula for the sum of a finite geometric sequence. S sub n equals, now we're going to go back to our summation notation or our sigma notation here. So the sum of a finite geometric series, if we add those terms, like all the terms together, in a series that ends, is equivalent to the sum of, or summation, or sigma, where I goes from 1 to whatever n is, as long as we know the first term, or find the first term, then we can multiply it by the common ratio to the I minus 1. That can be rewritten as a sub 1 times 1 minus r, common ratio raised to the n, divided by 1 minus r. So again, you need to know the first term, but once you know that or figure it out, then you can use this formula to find the sum of all the terms in a finite series. So this is a formula that you need to add to your list of formulas for this chapter. But before we do an example, I need to warn you that you always need to check your index here. This I, you need to check and see if that index begins with an I equals 1. Because it could begin with an I equals 0. And if it does, then we're going to need to adjust our formula to find the nth partial sum. We will do an example of that in a little bit, but I just wanted to show you, to warn you that you need to always be checking your index here to see that it starts with 1 or a 0. If it starts with a 1, you can use this. If it starts with a 0, we have to adjust it for a little bit. But let's go ahead and look at example 6 on page 579. Example 6 says find the sum of this geometric sequence, 4 times 0.3 raised to the nth power. This is not exactly like our pink up here, because the pink is the first term times the ratio, which our first term looks like it's 4, but it's times the ratio 0.3 raised to the nth power, where here this is raised to the index minus 1 power. So we need to figure out what our first few terms are, and then we can figure out what we can figure out what needs to go, what our first term actually is, because 4 is not actually our first term. The first term would be 4 times 0.3 raised to the first power. Our second term would be 4 times 0.3 raised to the second power. Our third term would be 4 times 0.3 raised to the third power, and so forth. We know by doing this that and we should know it anyway, that our ratio, our common ratio, is equal to 0.3. So I can write that down. My R is 0.3. but my first term is 4 times 0.3 raised to the first power, or my 1.2. That would be my first term. A sub 1 equals 1.2. So now that I know now that I know my first term and I know my r, I can substitute it into this formula up here, which would be my first term, which is 1.2, times 1 minus 0.3 raised to my n. In this case, my n is 12 because I'm going all the way up to 12, divided by 1 minus 0.3, which would be 0.7. So anyway, when I use my calculator and I simplify all of this, I get, it's not really equal to, it's approximately equal to, because I'm going to have to round it, 1.714. So the sum of adding all of these numbers together, the first 12 terms of this geometric series, gives me 1.714. If this sequence, or rather the summation of the sequence, would have had an index of n starts at 0 to 12, then I would have a 0th term, and I would have to adjust it. So I would have to figure out, instead of just figuring out my 4 times 0.3 to the first power, I would have to figure out my 4 times 0.3 to the 0th power first, which equals 4 times 1, which is equal to 4. And I would have to add that to my sum. I already figured out that my sum was 1.714, so really I would be saying this is the same thing as saying 4 plus my index is, instead of starting at, and I should have made that an n, not an I. My index was, instead of starting at 0, it started at, instead of starting at 0 now, because I've added my 0th term, so it's going to go from 1 to 12 of the 4 times 0.3 raised to the n, which is, we know, we solved it already, so it's going to be 4 plus 1.714, and because I'm adding that 0th term to it, it's now going to be 5.714. So that's why you've got to be careful when you look at the index, because if you look at the index, you need to figure out what the 0, if the index is n equals 0, then you need to figure out the 0th term first, and you're going to add it to the sum starting with the first term. And you will have problems like that on your homework. The last formula we're going to look at is the sum of an infinite geometric series, which I think is a little bit easier to use. Now this only works if your ratio, your common ratio, is less than 1. It's the absolute value of the common ratio is less than 1. So it can be negative, but its absolute value has to be, in other words, it's a fraction that's smaller than 1. If the absolute value of your common ratio is 1 or greater, then there is no sum, because you're going to go on forever and ever, and you're just going to keep adding and keep adding and keep adding. You would do a partial sum of a finite geometric series. A partial sum of an infinite geometric series would be a sum of a finite geometric series. And so you would go back to the other formula. But if this is an infinite geometric series and your ratio, your common ratio is, or the absolute value of your common ratio is less than 1, then you can find its sum. This formula is used to find, or to take a repeating decimal and turn it into a fraction. You can use this to find out what fractions go with what repeating decimals. And we'll do an example of that in a moment. I would like for you to study example 7 on page 580 on your own. We're going to jump over, so pause the video for a minute, look at that. But now we're going to jump over to example 8 on page 581, and we're going to do that one together. That one says to find the sum of 3 plus 0.3 plus 0.03 plus 0.003 plus, and so on, all the way to infinity. So this is an infinite geometric series. We can tell that our r is equal to 0.1 or 1/10, because if I take 3 and multiply it by 1/10, I get 3/10. If I take 3/10 and multiply it by 1/10, I get 3/100. If I take 3/100 and multiply it by a 1/10, I get 3,000, and so on. Recall that our nth term formula for a geometric series is the nth term is equivalent to the first term times the common ratio raised to the n-1 power. We're going to use that to rewrite this series that I have already up here. See here, I rewrote it as 3 times 0.1 raised to the 1 minus 1 plus 3 times 0.1 raised to the 2 minus 1, and so on. If I simplify that, that's really the same thing as saying 3 times 1 raised to the 0, which is just 3 times 1, so I'm going to leave it as that. And then 3 times 0.1 raised to the 2 minus 1 is 1, so that's the first power. I don't have to write the 1 there, but I'm going to just for now. 3 times 0.1 raised to the 3 minus 1 is 2, plus 3 times 0.1 raised to the 3, and so on. You don't have to do this. I just wanted to show you that you can rewrite it this way. What we want to do now is we want to add all these terms to infinity, find out what the sum is. So in order to do that, I'm going to use what I'm circling up here in green. That is my sum of an infinite geometric series formula. And I can see that by rewriting this, my a sub 1, my first term, is 3. I can also see that my common ratio is 0.1, so I'm going to say 1 minus 0.1. And then when I simplify this, I get the same thing as saying 3 over 0.9, which they have a common factor of 3. So this is the same thing as saying 1 over 0.3. Well, I don't want a decimal in my fraction, so I'm going to move my decimal one place to the right on the denominator to make it 3. That means I move my decimal place one place to the right on the numerator, and I get 10/3. Well, 10/3 simplifies. It's an improper fraction, so it simplifies to really 3, because 3 goes into 10 3 times, and 1/3. There is my mixed number, which is the same thing as saying 3 point. We know that 1/3 is 3, 3, 3 to infinity, don't we? And that's what I would be doing if I added this infinite geometric series. And you can also see that if I wanted to find the fraction that goes to a repeating decimal, I can use this a sub 1 over 1 minus r to find that. In fact, let's do another example like that. So let's see if we can find the fraction that that is equivalent to the repeating decimal 72 hundredths, or 72. So this is the same thing as saying 0.727272 over and over and over again. Or I can rewrite this as 0.72 plus 0.0072 plus 0.00072. I just have to move my decimal place 2 places to the left each time, because my r is 0.01. So now my first term is 0.72. 1 minus my r is 0.01, which when I subtract, I get 0.72 over 0.99. When I move the decimal over, I get 72 over 99, and both of those are divisible by 9. 72 divided by 9 is 8, 99 divided by 9 is 11, so 0.727272 is actually 8/11ths, and you can see that if you divide it on your calculator. Okay, so now I would like for you to pause the video and try these two problems on your own. And then once you've solved them, I want you to come back and see if you have solved them the way that I have. Please notice that in part A, you are finding the sum of a finite series that starts with 1 and goes to 10. And on B, you're finding the sum of an infinite series that starts at 0 and goes to infinity. So go ahead and pause the video now and work the problems. Okay, so now I would like for you to pause the video again and study the answers that I wrote up here and compare them to yours. I tried to show you every step, but in the blue one on A, I had to use a calculator to find the sum. On B, I didn't have to. Now that you paused the video and looked at it, I wanted to point out over here on B how you notice that the index starts at 0. So I needed to start at 1, so I needed to make an adjustment. I already knew what a sub 1 was from the previous problem, but I went ahead and wrote it up here again anyway. I needed to find a sub 0, That means when I substitute 0 in for 1/2, or for n, 1/2 becomes 1/2 to the 0, which is 1, and 1 times 16 is 16. So my 0 term is 16. And I needed to add that to the sum of n, the index starting at 1 and going to infinity. So I did that first. So I kept having the 16 go all the way down. And then I used my infinite geometric sum formula to find the rest of it, going from 1 to infinity, using the first term over 1 minus the common ratio, and solved it that way. Now we're going to do one more problem. We're going to do example 9 on page 581 together. Okay, example 9 on page 581 is about annuities. An annuity is a contract that's issued or distributed by an insurance company. It's not insurance though, but it's bought by individuals, and so somebody will buy annuities. They can either buy them in one lump sum, or they can put in regular payments for them to a company that holds their money, and then eventually that company will pay that money back in a regular payment to the person. But in the meantime, it's earned interest because that company has been borrowing that person's money. So people often use this for retirement plans. It is not life insurance. Life insurance is you put money into a life insurance company, and they only pay out money when the person dies. An annuity is when they pay out money when a person is alive. And again, this is kind of works for retirement plans, but we are going to read this example and solve it. It has to do with the sum of a geometric series. So it says a deposit of $50 is made on the first day of each month in a savings account that pays 6% compounded. It pays 6% and it's compounded monthly. What is the balance at the end of 2 years? This type of savings plan is called an increasing annuity. Now you will recall the compound interest formula that we have learned before, talked about before in here, where you would say the amount that you've earned is equivalent to the principal times 1 plus the interest rate divided by the number of times a year it's compounded, all of that raised to the number of times it's compounded total. That means in times the time, or in years. So it would be, in this case, it would be 12 times a year times 2 years would be 24. If we were to put $50 into a savings account and leave it there and not add anything else to it, this compound interest formula would work to say what the amount would be at the end of 24 months. But we aren't just going to put $50 in and leave it. We're going to put $50 in the first month, and it'll stay in for 24 months. And then we're going to put $50 in the next month, and it will stay in for 23 months. And then $50 again on the third month, and so it'll stay in for 22 months, and so forth all the way down. So you can see that this becomes a series. And so we want to know what the sum of this series will be at the end of 24 months, or the 24 payments. And even though we're adding $50 a month, we are still raising it to a power. So this is going to be a geometric series. So the first thing I'm going to do is find out how much my first payment will be worth at the end of 24 months. So I put $50 in, and then I have 1 plus my interest rate we said was 6%. So that's represented as 0.06. It's compounded 12 times a year, and in that case the first one will be compounded 24 times. So when I simplify this, this becomes 50 times 1.005, because 0.06 divided by 12 is 0.005, and then I add it to 1 to the 24th. Now, the next month I'm going to put $50 in. It will stay in for 23 months. So I'll have 50 times 1 plus 0.06 over 12 raised to the 23rd power, which simplifies to 50 times 1.005 raised to the 23rd. And again, the third time I put it in, it will stay in for 22 months. So 50 times 1 plus 0.06 over 12 raised to the 22nd. So that is equal to 50 times 1.005 raised to the 22nd. Now we could keep going on and on and on, but eventually we'll get down to the last deposit, which would be 50 times 1 plus 0.06 divided by 12, but it would only be raised to the first power because it's only going to stay in there 1 month. And so 50 times 1.005 raised to the first power. I apologize if you hear that hammering. My husband is working on something here in the house, so I can't help that. We are going to use the formula for the sum of a finite geometric sequence to find the total sum of all the deposits, all 24 deposits. I don't want to go through and figure out what each deposit is and then add them all together. I can take my shortcut by using the formula for the sum of a finite geometric sequence, which I wrote down here. S equals the first term times 1 minus the common ratio raised to the n over 1 minus the common ratio. So we need to say what is our first term. Our first term is going to be the last deposit. That would be our a sub 1. So we're going to let that equal 50 times 1.005. That's our first term. And we also need to know what our common ratio is. Our common ratio is what is raised to the power. So that would be 1.005. Okay? So I'm going to plug those numbers into this formula right here that I'm underlining. And we'll get S equals the first term, 50 times 1.005 times 1 minus 1.005 raised to the n, and in this case our n is going to be 24 because we made 24 deposits, and that 24th deposit actually earns the most money. Not the 24th, the first deposit earns the most money, but it's been in there for 24 months, so I said that backwards. The first deposit earns the most money, but that's not going to be our first term, that's going to be our last term. It's the one that stays in the most. I accidentally put an extra 0 in there. So anyway, now when I plug all this in my calculator and simplify it, I end up getting $1,277.96, or approximately that when I round it. So this is how much money I've earned in this particular annuity by adding $50 a month for 2 years. People that do this over a lifetime, they end up earning a whole lot more money, and then they can use that money, they can take it out for retirement purposes. It's not always going to be with an insurance company. It could be with a bank or with whatever. A lot of IRAs, I mean not a lot of, IRAs are annuities that people can pay into over a lifetime of working, and then when they retire, the money comes back to them monthly. So it's a great way to save some money and have some retirement money when you are older and no longer working, if you start young. So y'all keep that in mind for your futures. But anyway, that's just a little plug for adding into a savings account when you start working. So anyway, this is all that I have for section 8.3. I know it's a long video. Thank you for watching it. And now, hopefully, you have enough information to solve your problems for 8.3. Remember, I told you it won't be due Tuesday, but it would be a really good idea if you get started on it so that you can ask questions when you come back on Tuesday. Y'all have a good rest of the weekend.